Hello, everyone, and welcome back to Tech Talks, the science and technology podcast brought to you by Insight, the student media body of IIT Bombay.
Our second episode is also hosted by Prashant, who is an ex-chief editor of Insight, and today he is in conversation with Sriharsh Tendulkar.
Hi, I'm Sriharsh. I'm an astronomer at TIFR and NCRA. I search for bright flashes of light in the whole universe.
It's been a long time since we spoke, right? So,
Yeah.
you were definitely really interested in astrophysics quite a bit, like whether it was as part of the astronomy club or tech GC or what have you. And it looks like you stuck to that, right? So, like, where did you go from there?
That's right. After I was interested in astronomy even before IIT Bombay. My interest started growing through these high school competitions called the Astronomy Olympiads. And then I went through a couple of research projects. I worked under a couple of astronomers throughout India. And after that, I went to Caltech for my PhD, and I worked under Professor Sri Kulkarni, working on neutron stars and magnetars, trying to understand what their behaviors are. I've also built an adaptive optics system for the Palomar 60-inch telescope. And from there, I shifted gears to radio astronomy and moved to McGill University in Montreal, Canada, to search for fast radio bursts.
And I think that fast radio bursts is kind of what, when we were chatting, intrigued me as well, and I was really curious to understand more about it. So, how would you explain fast radio bursts to a layperson, just in simple language, and then we can go from there?
Absolutely. So fast radio bursts are fascinating. If your eyes were sensitive to radio light, you would see these bright flashes of light coming randomly from different directions in the sky, thousands of times a day. And some of these signals are as bright as your cell phone signals. Okay, except that they're not coming from a cell phone tower which is 10 kilometers away. They are coming from halfway across the universe. And so within a few milliseconds, they're producing enormous amounts of energy. They're producing more energy than the sun produces in a couple of months, right? So we don't understand how you can produce this kind of energy, store it, and then release it within a few thousandths of a second. The closest analogs we have, which are pulsars, which we know from our own galaxy, they are a trillion times less luminous than these fast radio bursts or FRBs. So these FRBs are an incredible puzzle for us to solve. We don't know what their origins are. We don't know how they're creating this much energy. And we would like to use them as probes to do some sort of a tomography, if you will, of the universe.
I see. And you said like thousands of times a day too, right? So it's not like they're not super rare occurrences.
No, they're not rare. And despite the fact that they're not rare, we did not know about these until about 30 years ago now.
Interesting. Why is that? Like, is it like lack of instruments that could catch it, or?
Yeah, absolutely. So a part of it is a computational challenge. So the way radio signals come from travel through space, whenever they interact with electrons along the path from the source to the Earth, they undergo dispersion. So lower frequency radio waves travel slower than higher frequency radio waves. So if you have a pulse which is emitted by an object and it has components in higher frequencies as well as lower frequencies, it will get smeared out as it travels through the space. And so you have to correct for this dispersion, and you don't know how much dispersion there is. You just have to search for different dispersion measures to find the pulse. So when people started discovering pulsars back in the 70s, there was no computation, and people tried to detect pulsars as much as they could. People only searched up to a certain level in dispersion because we had an idea of how many electrons there are in the Milky Way in any given direction. So we said, okay, there can't be anything outside it, so let's not search for it. We'll save on computation. But then in 2007, Duncan Lorimer just decided just off chance to increase the limit of this computation and search for higher dispersion measures. And they found this really bright burst in archival data from the Parkes telescope in Australia. And the dispersion from this burst, which indicates how many electrons it has gone through, suggested that it came from much further away than our galaxy. So the galaxy could have contributed only a third of the electrons that we are seeing in this signal's dispersion. And so that was the first puzzling thing. And people started wondering, how is this burst coming from so far away? It was really bright, and it seemed to be coming from really far away. So in the beginning, people were thinking that maybe this is something terrestrial, and Duncan Lorimer has mistakenly thought it to be astrophysical. People came up with lots of different.
So you mean like terrestrial as in like, is it just being caused by something on Earth, basically? Like by one of our...
Yes, absolutely. So there is a lot of terrestrial interference. So cell phones, TV stations can cause a lot of these bright flashes. And so I'll come to that in a moment. There's a very funny anecdote about that as well. I'll come to that in a moment. So people from 2007 till about 2013, people were not quite sure what to think of this Lorimer burst, as it is now called. And in 2013, there was another paper which published and showed that there is a cosmological population of these bursts. There are 5 more which were detected, which is great. But at the same time, there was another problem which was introduced, was that a couple of bursts were detected at the Parkes telescope itself, which seemed to be aligning at noon times in Australia. So around lunchtime in Australia, there would be a burst. And that is weird because the universe doesn't know about lunchtime in Australia, right?
Right.
So there was this very nice detective work that was done by a graduate student, Emily Petrov, who found out that if you open a microwave oven while it is in the middle of its cycle, and if it's a specific type of microwave oven which they had at the visitor center in the Parkes telescope, you can produce a similar signal. There are differences, but you can produce a fairly similar signal to what you get from an FRB. So that was a bit of a bummer, but we are glad to find that out. Since then, microwave ovens have been banned.
If I'm understanding this right, what basically happened is like there was a signal that was repeating with Earth's like rotation on its own axis, basically, right? Like if it's at lunchtime every day.
Exactly. So if it was at lunchtime, universe would have to know about it, but it doesn't.
Crazy.
Exactly.
And then so it turns out it was coming from the microwave.
Yeah, those signals, which were later called peritons, turned out to be coming from microwaves, but they had other distinct properties which distinguished them from real FRBs. So the real FRBs were safe.
Got it.
Yeah. So since then, we have, the rate of discovering FRBs has ramped up quite a bit. Earlier, people used to search in archival data and look for FRBs. And the first telescopes which were used for detecting FRBs looked at small parts of the sky, maybe about the size of half the full moon, to search for FRBs. But the sky is a big place. So even if there are thousands of them every day, the chance of getting one in your telescope's field of view is very small. So now the field is moving towards telescopes which can see huge swaths of the sky at the same time. And so your detection rate goes up.
And this is like, you're saying this started happening some 5-6 years ago, or you're saying this is state of the art today?
It is state of the art today. So we are now, over the past 2 years, we have been able to get to a point where we can observe huge swaths of the sky.
Got it. So let me go back a few years then. 2007 was really the first time when someone noticed this, and then even after that, it was a while before people found even 5 of them.
Absolutely.
And so by then, it sounds like everyone was already interested in knowing what these are, right? Like, or what's causing them. Was that the main mystery, or was it more like where in the universe it's coming from?
So both of these were a mystery. So we didn't know the exact distances to these objects, right? We can only estimate it from the dispersion measure, what we call the DM, which is a count of the number of electrons from us to whatever the source is. So we have a model for how much the Milky Way is contributing, and we have a model of how electrons are distributed in the rest of the universe. But there are huge uncertainties in those. So we didn't know what the exact distance was, and consequently we didn't know how much energy it is actually emitting. So you could have a lower brightness, a lower luminosity FRB which is closer to us, or a really luminous FRB which is further away. So that was one of the questions. And other than that, people are simply interested in what sort of emission mechanism could this be. So theorists were really excited. Theoretical astronomers came up with, I think, 80 or so different models for what FRBs could be. And I cataloged, I think, almost all of them in this FRB theory catalog, which we wrote with some colleagues.
So I was actually going to ask, like when someone in the field of astronomy notices something like this, right? Like that cannot readily be explained. Is part of it just like that inquisitive drive behind all science, where like we need to find out what this is? Or like are there other examples where something like this was found and then it led to improving our understanding of how the universe works? And is that what drives the community? That anytime we see something new like this, it could potentially add to our understanding of how things work in the universe?
Right. So it's both of them. The first is just absolute curiosity about what is causing these things, because it might lead to some sort of an exotic object, right, which we didn't know about. Or it could be exotic behavior from an object which we do know about, but we had never thought that this kind of a behavior would be possible. So all of these transients which occur, on a few millisecond time scales, and they're incredibly luminous, they need to have to be generated from compact objects. So either neutron stars or black holes or white dwarfs or something that is very small, because the sun can, for example, is huge and it can't change on very short time scales. So anything that is large cannot change on very short time scales. So we are probing the smallest, most compact objects which have the highest densities, the strongest magnetic fields anywhere in the universe. So you're basically trying to find new probes of matter in extreme conditions, right? And the other aspect, which is particularly for FRBs, which was interesting, was that because of this dispersion, you can probe how electrons are distributed in the universe. And you can also probe how magnetic fields are distributed in the universe, which is very interesting because we want to understand how magnetic fields arose in the universe in the first place, right? So we know that we can amplify magnetic fields, but we don't know how to generate magnetic fields from scratch. So there are a lot of different theories about how magnetic fields came about in the universe. And so these kinds of FRBs, if you have a lot of them and you probe different directions in the universe, you could actually try to understand how magnetic fields were generated in the first place, or how structure formed in the universe. So once people realize that you have this probe of the universe, which in the future could do this sort of tomography, people were really excited.
You were talking about how like it wasn't easy to detect these. Part of the challenge is just the expanse out there that you need to look in, right, to detect them. And when I was chatting with you earlier a few weeks ago, we were talking about your detection at CHIME. What exactly happened there? Like, what was the breakthrough?
Let me go back before CHIME a little bit. One of the things which happened was that using this telescope called Arecibo in Puerto Rico, this is the same telescope which recently collapsed, unfortunately. It was very sad for us. That was a telescope which was crucial in one of the biggest discoveries for FRBs in 2014. You see, most FRBs show up as single bright flashes of light. So there's a flash from a random direction and a particular dispersion measure, and you can look at the same location for a long time later and it doesn't repeat again. But there was this FRB which was discovered by Arecibo, and we were following it up, and we detected multiple bursts from the same location with the same dispersion measure. So we know that they're coming from the same source. So this was the first repeating FRB, which was really exciting, because now what it means is that you can go to other telescopes which are better at pinpointing the location of this FRB. So we went to the Very Large Array, the VLA, and we tried looking for this FRB and waiting for it to repeat. And then once it repeated, we were able to pinpoint the location and we were able to detect the host, find what is the host galaxy of this FRB. So it turned out to be this really tiny dwarf galaxy, which is weird because most if you expect that FRBs came from neutron stars or magnetars, which are very young neutron stars, you would expect that they come from these big galaxies because most neutron stars are in big galaxies. There are very few of them in these tiny dwarf galaxies, and so that was a big surprise, big shocker for us. And
So
and this was the first time
go
that we were
ahead.
able to directly measure the distance to the FRB and show that it is cosmological.
So show that it's cosmological as opposed to what do you mean?
One possibility was, FRBs could be just outside the Milky Way, right? We knew that it is sort of out there outside the Milky Way based on the dispersion measure, but you could argue, some people might argue that, oh, maybe it is just outside the Milky Way, but not really, halfway across the universe. This, it turned out, was about a third of the way across the universe, which is exciting for us.
Oh wow. I'm pretty sure I'll butcher the technical details of this, but you were mentioning how you would think it would come from like a neutron star or a magnetar, and that would belong in a large galaxy. Did I kind of get what you were saying there?
Yeah, absolutely. So
What's the specific like mechanism there? Like, so you have this neutron star, and then what leads to an FRB or a radio burst?
yeah, so we don't know exactly what
Oh, okay.
creates the FRB. So there are two things. One is you need an emission of energy, and then you have to convert that energy to electromagnetic radiation somehow. And there are a lot of different theories for both of these, both parts of this equation. Most of them involve neutron stars or magnetars because everybody agrees that we need strong magnetic fields to do the conversion of energy to electromagnetic radiation, which we see. But how exactly it occurs is a pretty open question. There are a lot of different ideas.
And then so you guys you were able to kind of pinpoint the location in a sense, like where is this coming from? And it turns out it's coming from a dwarf galaxy.
Yeah, we were able to pinpoint the location and we were able to say a lot about the kind of environment that this FRB was born in. So in astronomy, the environment in which you are to detect something can tell you a lot about the kind of object that it could be because galaxies have different neighborhoods. There are stellar nurseries where stars are actively being born, and you can see very young stars over there. There are neighborhoods which have had their star formation long time ago, and then what you see is old residual stars, and so you don't expect to see young stars there. So what we found was that this FRB was located in a very actively star-forming region of this dwarf galaxy. So it was more likely to be associated with a young star or a star that recently underwent a supernova and converted into a neutron star.
Got it. So whatever it is that's causing the burst, they've all happened like a while in the past, basically.
Yeah, the burst actually travels about a billion years, and it's detected within, the detection lasts only for a millisecond, which is crazy to think about. Yeah.
Right. Very cool. And I guess if if you're able to like kind of gauge the location, you pretty much know how far it has traveled, rather how long it took for it to travel.
Yes, because you measure the redshift of the galaxy, and that because we know from Hubble's law how galaxies are expanding, how the universe is expanding. So if we measure how fast this galaxy is moving, or that is to say, measure its redshift, then we can try to estimate the distance to it.
Yep. Yep. A lot of things that I read in college are screaming back into my head right now. Very cool. And then so like then you guys detected it, and I remember reading like one of the articles that you wrote about your finding, and I think you were talking about how like it was like any other day except it wasn't. And
Right. Yeah.
so was it like the very first day your telescope was operational, you caught the signal, or did I read that wrong?
Pretty much. I mean, so let me give you a background. As I said earlier, most telescopes which are built previously can look at only small parts of the sky at once. And since the discovery of FRBs, everybody wanted to look at huge parts of the sky and search for FRBs. So there was this telescope which is called the Canadian Hydrogen Intensity Mapping Experiment, that acronymed as CHIME, and it was made for the cosmology. So it was made to map hydrogen in the universe, as the name suggests. But what it did was it used to look at a huge swath of the sky as the Earth rotates, and the sky moves overhead. So this telescope was also, the design of the telescope was excellent for detecting fast radio bursts, because this is precisely what we need. So a group of scientists, including my postdoctoral supervisor, Dr. Vicky Caspi, they proposed to put a large computing backend underneath this telescope and then use the same data simultaneously for cosmology and for FRB detection. And that's where I came in. I was a part of the team which built the entire data pipeline and the computing aspects. We had been working for a couple of years writing a data pipeline that could take data from the telescope and then search it for FRBs and then make a detection and let us know that, okay, look, this is an FRB. And the first time we switched it on, we had switched on only about a quarter of the telescope, and we were all sitting in this windowless room at McGill, and it was basically a coding marathon, what we call a codathon, because we write a lot of software. And one of my friends spoke me like, "Does this look like an FRB to you?" And I said, "Yeah." And then everybody started poking each other like, "Look, this is something really exciting." And just like that, within a few hours of starting up our 1/4 of our telescope, we had detected our first FRB. And so we were really excited. And this was the first FRB which was detected in the frequency range that CHIME operated on, so between 400 to 800 megahertz. And before that, there had been no FRBs that had been detected at such low frequencies. So there was always this worry in the back of our mind that what if we never detect any FRBs at these low frequencies? What if they're all detected, at higher frequencies? So at 1.4 gigahertz was the standard frequency which all the previous FRBs had been detected at.
Got it. And then, like, it turns out you didn't have to worry about it at all, and you learned that.
No, we didn't have to worry about. Yeah, we didn't have to worry about it at all. Since then, we switched on the entire telescope, and we have been detecting hundreds of FRBs by now. So everything is chugging along.
And there are parts of what you just explained that that I only superficially understand. So you're mentioning how it's trying to map hydrogen in the universe. I'm sure that's like an hour-long discussion on its own, if not more. You guys realized this could also be great for FRB detection. Was that more because of how much of the sky it was looking at, or it was also that it was listening for a similar kind of signal?
It was basically because of the field of view, how much sky it can cover in one go. It was not set up to search for these bursts, for these particular signals at all. In fact, we had to do a lot of work to change the pipeline such that, apart from getting the kind of data that the cosmology team wanted, we could also get the data that we wanted. So it's the same data which comes in at the antennas, right? It is digitized, but then after that, what you do with it is completely different.
Got it. And that was the other part that I found really, interesting about what you said. Like, it starts off very much as a physics, cosmology problem, and then quickly turns into a data or software problem, like so many other things, obviously, today.
Yeah, absolutely.
And it sounds like a lot of work that you guys did was in fact in that space as well, wrangling with all this data that's coming in and figuring out how to squeeze out the useful information from it.
Yes. So a lot of our work, is, I hate to be sound cliched, but it is basically searching for needles in haystacks. We get 13 terabits of data per second from CHIME.
Wow.
And so then it is compressed down to 130 gigabytes a second, and that has to be searched for these bursts, which themselves last only a millisecond, right? So for every burst, and there are 5 or 6 bursts which are real FRBs every day, but you get a lot of signals from aircraft which are flying overhead, TV stations, cell phone antennas. Nowadays, even cars have Wi-Fi and Bluetooth for some reason, right? And so if there are cars passing by on the highway, you'd get these spurious signals. And so there are almost a million false signals for every real FRB. And so we have
Wow.
to go through all of that data and distinguish in real time with a very low false positive rate what what we are seeing. And so, and once we detect an FRB, we want to save the data, right? So we can't save all of this 130 gigabytes of data for coming in. So we have to make a distinction in real time whether we want to save a chunk of data where we think the FRB lies, and then we can, reprocess that data offline. But we have to make a decision right there and then.
Huh, that's that. Yeah, I wouldn't have thought of that. That makes sense. And is it not even like you can, I don't know, store maybe the last hour of data or something like that? It absolutely has to be look at it while it's in
Right.
flight and then discard it, basically.
So we buffer the data in RAM. So we have a huge RAM buffer actually distributed among 256 computers. So what we do is we buffer different kinds of data. One thing is to buffer the raw voltages, and we can buffer about 40 seconds of that, and that cost us a few $1 million in just RAM.
Phew. Hmm.
Let's probably not a few million. I think $500,000 in RAM. That's a
Oh, is
lot
that
of RAM.
all?
Yeah, and then there is the intensity data, which is the reduced version of the base of the raw voltage data, and we can store about few minutes of that, but that is compressed, so it is not as high quality.
Yeah, I mean, I think that totally makes sense. And then, like, a lot of the software, was it homegrown? Like, did you guys basically just sit and write things from scratch, or is there software that people like us would know that you actually ended up using for this purpose?
No, there is no software which can do what we've been doing. I mean, there are parallel efforts by other observatories, but each telescope has its own, tiny weirdnesses, and data formats are different. So it's easier to sometimes write things from scratch unless you're in a field which has matured enough that the data formats are standardized and everything.
Right. The reason I
Right.
ask
So
is,
yeah, so I was just going to continue that we did use a lot of the software developer tools though. So, when we are doing logging and log monitoring and, plotting things on, so we use tools like Grafana and Kibana, and Git is our standard thing for making sure, a team of 50 people can actually do development without breaking things. And as academics, generally we tend to code extremely badly, but thankfully we had program managers and project managers and actual programmers who could from industry who would tell us what sort of how good code is written. So documentation and unit tests and everything. But we implemented those in real life, which was really uh, good because now the code base is actually much better than what it would have been if it was just academics.
yeah, no, I like the candidness here about the academics and code. And we can edit that out later if you want to. By the way, if you don't want to
No,
go
no,
on
that's
record.
fine.
Uh,
No, that's fine.
so very cool. And then you guys found this in 2018, and then it sounds like you're saying after that the frequency with which you were finding these kind of increased, and now you have the entire telescope operational, so it's catching a lot more of these too.
Yeah,
Yeah,
absolutely. So we are catching a lot more bursts. We have now found more repeating FRBs, and we have started, finding distinct signatures of these of the bursts, which seem to be different between repeating FRBs and other FRBs. So we are not sure whether they are different populations yet, but it seems like they behave slightly differently. So repeating FRBs seem to have these complex bursts with multiple subcomponents, and they tend to show this drift in frequency. So they show up at high frequency first, and then the second subcomponent shows up at slightly lower frequencies. The third subcomponent shows up at slightly lower frequencies. So what we call a science reporter once very nicely described it as the sad trombone effect. You have these falling notes of a sad trombone like bah, bah, bah.
right.
Yeah, so we call it the sad trombone effect, and we see it mostly for repeating FRBs and not for what till now are single FRBs. So these single FRBs could eventually repeat. Maybe 100 years later, you might see another burst, but we can't rule that out.
Got it. And the data challenge still remains, right? Like you're still looking at a lot of data to find these signals. Outside of your field, that whole field of making sense of data has changed a lot, right? Like over the last multiple decades, but definitely in the last 10 years as well. Do you see some of those learnings from outside coming into your field as well? Like I'm referring to things like using neural networks or machine learning to identify patterns.
Yeah, absolutely. So we learn a lot from people outside the field, and we do use machine learning. I wrote some of the code which uses machine learning to identify aircraft signals from actual astrophysical signals. One of my students who did his master's at University of British Columbia, he also wrote a neural network code to do the same thing, do a slightly more advanced thing. So we have been using a lot of that, and there is, we still keep improving our pipeline to do better.
Very cool. Yeah, no, it's interesting how like state of the art in one field can help state of the art in the other.
Absolutely.
And I mean, this seems like a prime example of where some of the advances in machine learning can help in physics. And so, where are we now then? Like, are we any closer to figuring out what's causing these? Like, it seems like we know where they're coming from.
Yeah, so we have identified the host galaxies for a dozen. We, as in not CHIME itself, but the broader astronomy collaboration.
Right.
We have identified about a dozen or so host galaxies, and just recently, earlier this year, there was a paper which showed that the distribution of electrons, which we can infer based on these host galaxies and their distances and the dispersion measures, does actually account for what was called the missing baryon problem. We expected from cosmology that there was about 30% of the matter which was missing, and we expected that it was between galaxies, but we had no firm proof of that. And using these about a dozen FRBs, astronomers were able to show that it actually does exist in a way that we expect it to.
Got it. Something that occurred to me when you were talking about these problems, and earlier when you were discussing like expansion of the universe, like either with FRBs or related problems, are all these things kind of adding up to helping us understand more about either how the universe is formed or where it's going? Like, are there fundamental questions that this helps answer?
Yeah, so as I mentioned, understanding the distribution of electrons and how the structure of universe formed is very important. Understanding where magnetic fields came from is quite fundamental. It's going to be a long time before we are able to answer those questions, because they assume that we'll have millions of FRBs and we'll have localized all of them, and we'll have pinpointed their host galaxies and measured the host galaxy distances. That's a very, very data intensive task, and we are nowhere close to being able to do that. But eventually, there is hope that we can do this.
Got it. So, meanwhile, I guess it's basically the quest continues, so to say, right? Like we just keep looking.
The quest continues. Yeah. So, in fact, with CHIME, for example, we are building these outrigger telescopes. So, they would CHIME on its own cannot localize an FRB very well. So, it can say that it's in this region, which is the size of about half the full moon, or just a full moon. But that is not sufficient to tell us which galaxy it is coming from, because there are literally thousands of galaxies in that region. So what we need to do is to have other telescopes which are built further away, which will also detect the FRB at the same time, and then you can triangulate the position of the FRB very precisely. And once these are built over the next couple of years, we will be able to precisely localize every FRB that CHIME detects. And other telescopes are doing similar efforts, and the hope is that we'll get a huge population of well-localized fast radio bursts.
Got it. Very cool. A lot of times when you hear of such findings and they make their way to like the popular press, there's always this cliched popular suggestion that, hey, maybe it's aliens. So I guess we can keep continuing with those speculations until you guys figure out what's actually going on.
Yeah, I wish you wouldn't, but I can't
You
stop
can,
people from thinking. So
yeah, exactly. I mean, we're just having fun, Well, we know that
yeah,
you guys are on
absolutely.
the job. We're just killing time meanwhile. Very cool. And so probably like if I wanted to read up a little more on this or learn about the field, and maybe if I went 10 years back and this was a field that I wanted to get into even, like how would someone go about doing that?
Right. So there are a lot of very good popular science articles on FRBs now, and a lot has been written, in the Scientific American, for example, and National Geographic, which are articles which are intended for non-scientific readers or people who are interested in science but are not necessarily astronomers. So those would be good places to start. If you're a rising undergraduate or a beginning graduate student, I would strongly encourage you to read the academic papers directly. There are some very nice reviews which you can read to understand what the challenges in the field are and where the field is going. Apart from that, I would strongly encourage, if there are any students, I would strongly encourage them to strengthen their tools, so which is programming, understanding of basic physics, and also to get in touch with astronomers, including myself. If you're interested, we can, there are a lot of things that can be done, and the field is growing.
Very cool. Yeah, thank you for that, Shriyas. This was fascinating to discuss. I think I told you as much when we first spoke about it, and which is kind of why
Mhm.
I was pestering you to do this chat. So thank you for that.